Hi everyone, I hope you're doing well today. This is Mr. Hernandez and let's get right into our lesson. Today we're going to be looking at simplifying radicals, but really we're going to be focusing on when you're dividing radicals and rationalizing the denominator. So what that means is rationalizing the denominator when you have like a square root of mumbo jumbo over like the square root of mumbo jumbo. We hate having square root in the denominator whenever we're working with fractions. You don't want things such as square roots or imaginary numbers in your denominator. And so we have these tools to help get those kind of numbers out of our denominator. Makes the problem a lot easier to work with. All right, so let's go ahead and jump into our first problem. What we have here is says the square root of 3xy squared over the square root of 5xy cubed. All right, so actually what I want to do here is I'm going to write this all under one big square root. So it's going to say 3xy squared over 5xy cubed. And I'm going to do this and then I'm going to go back to one, but the reason I'm doing this is to see what cancels out. So we're going to switch it over here to red, and what we're going to notice here is that these x's cancel out, and then whenever we have like y squared over y cubed, you divide out, and what happens is you do subtraction for your exponents, and so you end up with 1 over y to the first. So just 1 over y. So that's why we do that right there. And so what becomes of this is we get the square root of 3 over 5y. So actually that makes rationalizing the denominator so much easier. This is a bit of a different method than what I went over in class, but you know, both still kind of work out. So from there, I'm going to put it back into two square roots. So the square root of 3 over the square root of 5y. And what we're going to multiply is, and this is where we're rationalizing the denominator. So what I need to realize is I need to get, so my index here is 2. So I need to make these 2s, or something divisible by 2. Well, 5 times 5, I know, well, 5 times 5, well, that gets me 25. But another way I can write 25 is 5 squared. So those things are equivalent. So that's how I'm going to write it. And now when I look at this, I know that's a completely different way than what you're used to looking at 25. But what happens is like square and square root, they cancel out. And I'm going to do the same thing times with the y. So y times y, well, that'll get me y squared, which is what I'm going to end up needing. So actually, I need to go erase the square that I accidentally put in there. Let's see. Because it's not squared, it's just to the first power. All right, but that is what we're going to get out here in a second. Over, and what we're doing is anytime you're rationalizing the denominator, you are multiplying by 1. So we're going to multiply it by another square root of 5y. All right, so I'm going to move this over here to the side a little bit more. There we go. And we're going to get back into it. So here we're going to go multiplying straight across. So 3 times 5, that's 15. And then y, there's nothing to multiply in here, so we're just going to hold on to it. 15, square root of 15y. Then in my denominator, I'm going to end up with the square root of 5 times 5. But another way to write 5 times 5 is 5 squared. And then y times y, which is going to say y squared. So what happens from there? Well, in the numerator, we're still sticking with the 15y. We'll simplify that if we can. But in my denominator, I end up with 5y. And so that finishes out this problem, because what I really want to check is, is the square root of 15, is that divisible by any perfect squares, 4, 9, 16, anything like that. And in this case, it can't be simplified. So my numerator has a radical and my denominator does not. And that's when I am done. So this is the simplified version of what we started with. Now we don't have this radical in your denominator. All right, so let's move on to the next one. All right, and what we have here is we want to put it under one big one again. So one big one, so we can get things that cancel out first. So 5x to the fourth over 2x squared y cubed. And so what you might notice here is 4 over 2, so those are going to be 4 minus 2, so we're going to end up with x squared in my numerator. So it's going to say 5x squared in my numerator over 2y cubed. And so now it's the x in my denominator is gone because 4 minus 2. Left the 2 up here and as my exponent, and I still need that square root. So what we do here is split it up into 2 now. So square root of 5x squared. I know it's weird going back and forth, but this is the notation that you need. This is the work that you need to show. Square root of 2y cubed. All right. So square root of 5x squared over square root of 2y cubed. And every time I'm doing this, I'm always asking myself a question. And that question I'm always asking right here is, what's missing? Ooh, come on, computer. What's missing to make a perfect square? So I put square in parentheses right there because it's not necessarily always going to be a square. You could have a cube or a fourth root, but that's what we really need to check, actually. Question mark. So that's what we really need to check. And so what's missing? That's the rationalizing your denominator. So I'm going to multiply here, and I need to see what is missing. So I need things to have exponents of 2. Right now this has an exponent of 1, so I need to multiply by 2. Here this has an exponent of 3, but that's not divisible by 2, so I need to add another exponent in here. And so y cubed times y, so y cubed times y, that gets me y to the 4th, which is going to be divisible by 2. And write the same thing up here in my numerator. All right, now I'm ready to multiply everything out. So in my numerator, 5 times 2, that's going to get me 10. And then x squared, and then y, over 2 squared and y to the 4th. And that is all square root. And then what that is going to equal to is, well, let's simplify my numerator now. So square root of 10, again, thinking perfect squares, square root of 10 cannot be simplified. And but the square root of x squared, that's just x. And remember, anytime you start with an even index and you get an odd exponent, so the 1 that we got right there, you have to put absolute value around it. All right. And so we still have absolute value of x 10y. The 10y is still there. Over 2y squared. So the square root of y to the 4th is y squared. Now it doesn't look like anything else cancels out here. So this would be my final answer. I have no radicals in my denominator. The denominator is rationalized, which is what we are focused on here. You can't simplify from here on out. Don't go crossing out the y's here because this is still under the square root. You cannot touch those y's because this one is still under the square root. All right, moving on to our next one. If you're feeling confident about this one, I think you're totally ready to go. Same concept is going to apply, but we're going to jump into it right here. All right, so what I want to do, how we're going to start this one out, put it under one big one, because what I notice here is that the 14 and the 7, those are going to cancel each other out. Not cancel each other out, obviously, but we could simplify it before going on. So cube root of 14 over 7x squared y. Well, 14 over 7 is 2, so we're going to get that out of there. So it's going to equal the cube root of 2 over x squared y. Okay, and then we're going to say we're going to split it up into two different cube roots. So cube root of 2 over the cube root of x squared y. Now, switch my color here. We want to multiply by rationalizing your denominator. Multiplying by 1. Coolest thing about math is you can multiply by 1 and change everything up. So it's going to be cube root. Now again, what do I need to make this one a perfect cube? Well, it says squared, that's not divisible by 3, so we need to get this to say 3, and to get it to say 3, we're going to multiply by x. And here, I need an exponent of 3 or something divisible by 3, and to get this one to say an exponent that's divisible by 3, we're going to multiply by y squared. Because y times y squared is y cubed, which we will get. And then the same thing in my numerator, the cube root of x, y squared. So back to blue. And we're going to multiply everything out underneath our radical signs. So that's going to equal to the cube root of 2 times x, y squared in my numerator over the cube root of x cubed, y cubed. And what we get from this is going to be the cube root of 2x, y squared. Doesn't look like anything simplifies there, over x, y. And now I have no more radicals in my denominator, so that would be your final answer. We got one more example here. Again, go ahead, tackle this problem if you think you're ready. This is a little bit more complicated, but you have the skills to go ahead and do it. So let's go ahead and get started. What I'm going to do here is I don't like the 3 and the 2 being out here. And so actually I'm going to put it back in. Well, the only way to put it in is if it says 3 squared in here. Basically, that's what you took out before. And so I'm going to put that back in here by saying the square root of 3 squared times 11 x cubed y. So the 11x cubed is still in there, but if I have the square root of 3 squared, that's what gets me the 3 back on the outside. Over the negative sign right here, that'll be okay to leave out here, so I'm going to leave that out here, the negative. And then the 2, I want to put it in the exact same way. So 2 squared, 12x to the 4th y. Alright, and now I'm going to put it under one giant square root just to see what cancels out. And I'm also going to multiply or find these exponents and multiply them out. So I'm going to get the negative. Well, 3 squared, that's 9. 9 times 11, that's going to get me 99. X cubed y over the square root of 2 squared, which is 4, and then 4 times 12, that gets me 48. X to the 4th y. And now I'm going to put it under one big square root. The negative sign is still out there. So 99 x cubed y over 48 x to the 4th y. What I want to do here is I want to start simplifying. And so what I might notice, which you might notice, before we've even rationalized the denominators, that these y's cancel out. And I'm going to end up with 3 minus 4, which is going to leave the 1 in my denominator. So the 3 and the 4, that's going to leave me with just in my denominator, so equal negative sign, square root around everything. In my denominator, I'm going to have 48x, and in my numerator, I'm just going to have 99. Let's see, does 99 simplify to anything? 99 over 48. I'm just going to pull out my calculator right here. 99 over 48. Nope. Let me see, does that reduce into anything? 33 over 16, actually. See, I would have not gotten those numbers, but we're going to get those with the calculator. So equals negative square root 33 over 16x. Alright, so 33 over 16x. And now I want to split it up. There's nothing else I can simplify, so split it up now. Negative square root of 33 over the square root of 16x. Same question that we were asking before, which was, what do I need to make these perfect squares? Well, 16 is already a perfect square. So I'm going to actually leave it like that. But x to the first, I need to multiply by another square root of x. So square root of x up there too. And so we're going to get this equal to the negative square root of 33x over the square root of 16x squared, which is equal to the negative square root of 33x over 4x. All right, and so what we have here is our final answer. Now you might be wondering, like, all right, why does this one not come out to be an absolute value? And the real reason is because when we start, we have x to the fourth. So x to the fourth is already going to be reducing down. It's basically anytime you have an even power, you're going to have an even number. So there's no reason to make this an even number with absolute value. Not an even number, positive number. So there's no reason to make that there with an absolute value, because no matter what, the x is going to have a positive value because it is to the fourth. So if you were wondering about that, that's your reason why. But that general rule of whenever you start with an odd, or start with a even index and you end with an odd, that's you can always put them in. I'm not going to take any points off for that. All right, so that finishes our lesson. I know that last one was kind of interesting. It really encompassed everything that you've done to this point. But if you have any questions, please don't hesitate to contact me. My name is Mr. Hernandez, and I'm always here to help.